wonderful honor to introduce our next ISBA lecture by Christian Robert, who is one of the massive contributors to MCMC and among many other things has written a wonderful book, The Bayesian Choice, one of the few technical statistics books that are actually really a pleasure to read. I really enjoyed it. But somehow off lately he has abandoned the exact and beautiful things, and he starts to do things approximately. And he's going to tell us about this. Approximate Bayesian computation, the ABC, advances and questions. Please, Christian.
Okay, Peter, thank you for this approximative introduction. First, I want to thank the organizers for giving me this opportunity to talk about ABC. It's a bit of paradoxical that it comes in a Bayesian Foundation session, in the sense that it's only approximately Bayesian, so it cannot be truly foundational. But actually, I mean, first I propose this topic because this is my current area of interest. But also I think that when I was trying to prepare those slides from previous lectures, I saw that there could be something slightly deeper than just being approximate, in the sense that, to link with Mike's talk, as we are facing harder and harder problems, larger and larger data sets, it's getting harder and harder to stick with the traditional model that is completely defined, that we know from A to Z except for the parameter. And therefore, dealing with approximate models or approximate methods may be a vision of the future and not only a side occupation for us Bayesians. The first thing is, this happens at like the worst of times, in that my principal co-author, George, died last week. And so I'd like to dedicate this talk to his memory and mention that on Wednesday, we're having a memorial session at lunch break, to which, of course, everyone is welcome to participate and talk stories about George and his wonderful personality. Now, this talk tries to avoid too much technical stuff about computations, and rather trying to focus on the thing I mentioned at the beginning, namely that this could be a different perspective on a new type of inference machine. So, I mean, I'm not trying to oversell the method. It has its drawbacks, and I mentioned them during the talk. But at the same time, it allows to process at a reasonable cost harder problems than found previously. I'll get rid of that. Yeah. Okay, so I'll just give a few words of introductions, then describe what is ABC, and then on the last part, hopefully reaching there, I'll link ABC with inference and what I mean by that. Okay, so to motivate ABC, let us start with the basics. We have a Bayesian problem of inference, and for instance, we want to compute an integral that is related to the posterior, and we cannot compute this integral. Okay, so that's the usual stuff, and therefore we process the issue by producing a sample from this posterior and using the basic Monte Carlo approximation that has all the standard properties if the function we want to integrate is regular enough. Okay, so that's standard stuff. Of course, to do that, we need to provide this sample from the posterior, and this is often impossible or very inefficient if we don't know how to simulate efficiently from this posterior. And therefore, there are many ways of getting around that, and one that has been around for as many years as Monte Carlo actually is importance sampling, where instead of simulating from the posterior, you take a proxy, that is this density Q, and simulating from this density, you re-express the problem, especially the integrals, against this density. And therefore, if we can produce a sample from this importance sampling density, given that we are free to choose it, then we can provide an approximation to the integral by re-expressing this integral as this expectation. Okay, and therefore, exactly for the same reason, we have the same convergence properties. Now, of course, to do that, we need to be able to compute pi over q, and in most Bayesian problems, we don't know pi exactly because we are missing the normalizing constant. And this is not such a big deal because we can estimate the constant for the same price, for the same cost, and divide this average by the average of the weight. And again, we get the same type of results of law of large numbers and central limit theorems. But this again imposes some constraint on the problem, namely that pi at least should be known up to a constant. And when pi is not available up to a constant, we are suddenly facing a problem of a much higher difficulty, and to some extent, a problem that sounds unfeasible in the most realistic situations. And so this will lead to the introduction of ABC. And again, we can see things from different perspectives. Either we are dealing with a mere computational problem, and mere is to be put between quotes, but because it's a computational problem, the core of our job is not affected, and we can hope that a better computer or a better method will appear and solve the problem. That's the optimistic side. The pessimistic side is that we may have to wait too long for this solution. Now, there are other ways of looking at the problem, namely that the very nature of the model, the fact that it is not a tractable model in the sense of providing a closed form density or a computable density, pushes for different inferential approaches, and to leave the standard Bayesian path for a different inferential approach that, if you're optimistic, can be repatriated within the Bayesian realm, and if you're pessimistic, that is incoherent because it's not exactly Bayesian. And a middle ground is to say that we may still be Bayesians, but we are dealing with different types of estimators and methodologies. And again, the bright side is that because it's still within the Bayesian approach, it's valid and coherent. And if you're not that optimistic, it may lead to cases where it's not coherent because, for instance, it's not convergent. Now, just a side issue that actually relates to ABC, and that's more like an historical background on the issue. There are a lot of connections with the introduction of ABC, between the introduction of ABC and some solutions that have been developed in econometrics. And in a sense, we are not always paying enough attention to what's going on in econometrics, although, I mean, the two fields are statistics and econometrics are close enough. What happens is that in the past 15 years at least, there have been ways to deal with complex econometric models that prefigured ABC and related simulation-based techniques. And so I will just mention a few here. in case you have not seen them, and if you have, in case you have seen them, to make the link with ABC. So, and for instance, the simulated method of moments is such that because you cannot compute a likelihood, for instance, you produce pseudo-observations from your Hume model with a given value of the parameter theta, and you try to fit the best theta in terms of the simulated data when compared with the original data, y0t. So that's one approach. Given that it depends a little too much on the series, and so it looks at the difference between each term of the series, an alternative is just to look at one statistic based on the series, and for instance, to take the average of the observations minus the average of the simulated observations. And if you know already ABC, you can see that there is a perfect link there. And then a bit broader and more ambitious is a method of simulated moments, to distinguish it from the simulated method of moments, that goes a bit further and uses first a statistic K, for which we can find an unbiased estimator of its expectation and compare what we observe, the K of yt, again with a simulated version that may be repeated in order to reduce the Monte Carlo variation. And this distance is arbitrary, but we again pick a parameter theta that tries to bring what we observe through some prisms, through some change of perspective, because K is only a statistic, it's not a whole vector, and an approximation based on the knowledge of the method. And then comes, I think, the most interesting of the group, which is the indirect inference approach that was introduced by Gouriot et al. Namely that they go even farther from the assumption they have on the model by using estimators that rely on a pseudo model that is not necessarily true, but using the model behind the picture, behind the scene, they try to find the parameter theta that brings this estimator of the wrong model as close as possible to an estimator based on pseudo data using the true model. So it sounds quite convoluted, but it allows for processing situations where the true model is truly a complex thing, where all you can do about it, the knowledge you can use from it, is only simulating pseudo data. Now, there are, again, many ways of implementing this principle. There are many choices to calibrate the method. For instance, once you pick a pseudo model, you can use directly the maximum likelihood estimator for the pseudo model, that the pseudo maximum likelihood estimator, and from there compare your beta hat at the observations with beta hat at a sample of pseudo observations. Or else, in a slightly related way, you can use the score vector in the same perspective. Now, does it work? Well, if you look at the creators of the method, Guerrero and Montfort, they are rather vague about the cases where it works, but they have this interesting sentence that we will find again in ABC, namely that, of course, beta must contain enough information to recover the parameter theta. And so in a sense, within this construct, theta must be the equivalent of identifiable. And then they get to this interesting sentence that we will recover later, namely that the best case, if I interpret their words, the best case is when the parameter theta is just identified, namely when the pseudo-model is parameterized in the sparsest possible way, not to induce extra dimensions that would slow down convergence and lead to more inefficiency. So that's an interesting feature of indirect inference. Of course, there is a lot of arbitrariness. The justification in the economic literature is justification of consistency and the convergence of those estimators at a given speed. So we cannot recover much for our problems with a given sample size. But there is an interesting follow-up to the indirect inference paper by Arnoldo Frigiesi and Egland in JRSSB in 2004, where they try to have a more practical evaluation of the method by comparing choices of pseudo-models and of estimators in a variety of situations. And they came with the conclusion that beta hat had to be dependent on theta. So in statistical terms, if you pick an ancillary statistic, it's not going to help very much, which makes sense. But at the same time, once you get information about theta, that is when beta hat varies when theta varies, you must have as concentration as possible in the distribution of beta hat of theta, which again makes sense because the more concentrated it is, the easier it is to get the relevant information about the parameter theta. There will be a talk in one of the ABC sessions about the use of indirect inference in connection with ABC by Chris Duvrendy. Now, another approach that I put under the hat of econometrics, although it's broader than that, is empirical likelihood. And originally, it's not a method that is directly related with simulation, nor with ABC, but I will make the link in a minute. Empirical likelihood is another way to process complex models where you don't want to make all the assumptions you need to create a complete model. Instead, you introduce a parameter that is your parameter of interest, and linked with this parameter, you define expectations that define the parameter. So essentially, you introduce a parameter that either defines moments or behaviors of the data that are of interest to you, and you create a function of the data and of this parameter so that you get a pivotal quantity, h of y and theta, whose expectation at theta is 0. Okay. So for instance, if theta is the mean of the y's, you just get e of y bar minus theta equals 0. And based on this definition of the model, which is not a model, but just a collection of features about your problem, you define the empirical likelihood by, well, you start from the empirical likelihood that puts weights 1 over n to each point in your sample, and you start twisting the weights so that the constraint is fulfilled, is satisfied. And so you must get sum of the pi h of y I theta to be equal to 0, which is a translation of this constraint. Okay, and this is not new. This is due to R. Torban in the late 80s, and it has not been very much connected with the Bayesian approach, although this is coming, and in particular in this meeting, there will be an entire session dedicated to empirical likelihood and the Bayesian approach. So, I mean, this is the illustration in the case of the mean. You start picking the weights so that the weighted average of the y's is theta, and optimize the product of the weights to get the largest possible empirical likelihood. And the more theta, the farther theta is from the true theta, the one that corresponds to the data, the harder it is to fit this constraint, and therefore the smaller the product. Okay. Now, what is the connection with ABC? Well, you can, starting from this perspective, whether the model is totally provided or you only want to make a few assumptions about your model and you don't care about the whole construct, you could create a simulation approach that rely on that by simulating theta i's from the prior or from an alternative importance function, and then create regular importance weights, except that you use the empirical likelihood rather than the original likelihood, again, whether you can compute it or not. And we played with this notion in a fairly recent paper to try to compare that with more standard ABC. And in both dynamical models and population genetic examples, we found that this was providing a much more stable evaluation to the likelihood than the regular ABC, the state-of-the-art ABC. So why is it ABC in that case? Well, it's approximate, just like this picture that we don't know really if it's Bayes or not. It's Bayesian. This we know it's from Bayes. This is the picture you get in this paper. It's Bayesian because, well, you simulate from the prior, so how more Bayesian could you be than that? And it's computational because you provide a sample that tries to approximate a certain target, as in this example where it works beautifully. I don't put a picture of the example where it doesn't work. All right, now, is it really Bayesian? Well, the only justification of empirical likelihood, like the whole collection of those econometric methods I presented, is that it's validated by the sample size growing to infinity. So is it really meaningful for us? That's debatable. The second point that for me is more important is that we are giving an approximation to the truth, whatever the truth is or means. And the trouble is that this approximation is very hard to assess by itself. So it means these methods are good approximations methods. Sometimes they are the only way to provide an approximation. But unless you run extensive simulation of a magnitude that is higher than the one you need to produce the approximation, you don't know really how far you are from the truth. And that's a big drawback. But again, in realistic situations like the one we face in population genetics, this may be the only valid implementation, because otherwise we would have to wait weeks or years, or we would have to use alternative models that do not provide the same amount of information. Okay, so this was just the introduction. So now I can reach the ABC per se, the genuine ABC. And I just have 2 words about the genetic background. The main reason is I don't want to make more of a fool of myself by speaking about genetics, so play safe and don't say anything. The second thing is that some of the talks we will be listening to in the week are connected with genetics, so they will know what they talk about. So, I mean, ABC, the genuine ABC, started in practice in population genetics about 15 years ago to deal with genetic scenarios relating populations to a common ancestor, where people were interested in the parameters driving the divergence between populations. And so there were a few parameters. We're not talking of big data, but theta. Theta could be as small as 2-dimensional or 1-dimensional, cannot be smaller. But these parameters were hard to derive because the likelihood had a very funny shape that depended on this population tree towards the most common ancestor that was huge and difficult to integrate. And this is a kind of example that the people I worked with were analyzing, where you had several tribes of pygmies in Western Africa. And the question the biologists were considering was about the origin of those pygmy tribes, namely whether related together and they issued from a branch from the non-pygmy population earlier, or the split was more complex. And so there are these kind of scenarios where you just have to look at the colors. These different scenarios they wanted to compare, and again the trees as the topological structure was interesting, but the actual tree of going to the most common ancestor was not. And so this made a difficult problem because the likelihood was not available. So that's how it started. That essentially we were in a kind of missing data problem, but there was so much missing data that this integration was not possible, or it was only possible in the simplest of cases, and otherwise it would have taken too long to compute. So we are going back to the same problem, namely that we have a likelihood function that in many cases is completely defined. You know it entirely. In other cases, as in empirical likelihood, you just know a few features, but essentially you know it entirely, and you don't know what to do with it because its computation is impossible. And so therefore, you cannot do MCMC, you cannot do importance sampling, you cannot do any of the regular simulation trick that we are so used to. And so the question is whether we give up any approach, because essentially you have to change the model. It's not like another method is available, or you have to settle for a degree of approximation, and the question is how much approximation is it? And so, in a sense, we have to do ABC stands for almost Bayes can, in the sense that it's not Bayes almost can, but it's almost Bayes can. Okay. So, just after such a long wait, you can see what is ABC. You have a target that is, say, a Bayesian target. So you have the prior and the likelihood. The likelihood cannot be computed, but you know how to define it as a construct. So you can produce simulations from this likelihood. And the trick is related to this very basic, although essential, property that if you simulate from the prior, theta prime, then you simulate pseudo data from this model, Z, and you wait until Z is equal to Y, the observed data. The time you get out of this loop produces a theta prime that is exactly from the posterior distribution. Okay. That's easy to prove. Just look at the distribution of the outcoming theta I. It is the prior times the probability to accept, and the probability to accept is f of y given theta I. So it's accept reject 101. But it was noticed in 1984 by Don Rubin, and also in 1984 by Peter Diggle and Grayton, more in a conceptual way than for Don Rubin than in a practical way. But as a representation of what is a posterior distribution, the posterior distribution uses a prior as a prediction of a population, and in that case, it weights this simulation by pseudo data that must mimic the true data. And so Arnold's paper is quite interesting because it gives a fairly intuitive approach to Bayesian statistics. But of course, in practice, it was only till 1997 that it became a practical tool. Now, is it practical? Well, as I wrote it, it's not practical because waiting for Z equal Y means that this is an event that must occur at a human scale. You cannot wait billions of years for Z equal to Y. And therefore, the A in ABC is drifting away from this exact representation of the posterior by allowing for some tolerance around the data. And so you don't accept only when Z equal to Y, but when Z is close enough to Y, namely when a distance between Y and Z, or a pseudo distance, is less than a certain epsilon, and epsilon is the tolerance that you're ready to tolerate, and actually in practice, this is the tolerance that you're forced to tolerate if you want to solve your problem before you retire. Now, of course, this produces an approximation, and this approximation means that you're not simulating from the true posterior, but from a convolution of this posterior by this tolerance zone. Okay? And that's the price you have to pay, or you should pay, for solving approximately the problem. Okay, so the algorithm you can write it in a few lines. You simulate from the data, simulate from the prior, sorry. You simulate pseudo-data conditional on this value of the parameter, and you wait until z and y are close enough. Now, there is another degree of approximation that is found in most cases, namely that you cannot wait for the whole data to be close to the whole pseudo-data. And so you force this proximity, this closeness, to occur in a reduced space through the use of statistics that are called summary statistics, which doesn't mean anything because they are statistics, that is transform of the data. The point is that they are usually not sufficient, so they are throwing away some part of the information content of the data, but paradoxically, as I will explain in a minute, this is almost necessary to do anything useful with this method. And so the regular ABC algorithm will pick not only a distance and a tolerance, but also a summary of the data through this summary statistic, eta. And again, this leads to an approximation of the posterior, because so we get this convolution of the true posterior with the z, and the belief is that if epsilon goes to 0, we should get back to this pi of theta given 1. That is, if we put enough computational effort, we shouldn't be too far from the truth. Okay, so I'll just skip these slides. There are ways of proving that essentially if epsilon goes to 0, you do recover something that is close to the posterior, but you have to make some assumptions. So there are two ways I had to prove that. That's not very important because actually it's not, of course, always true. And in most cases, because we are using insufficient statistics, we cannot recover the true posterior. At best, what we could recover is this pi of theta given eta of 1. Okay? Now, this is the best we can hope for, but if we get to this extreme and caricatural case where eta is ancillary, then we don't recover anything at all. The best we can hope is a prior. Okay? And I made, this is a typo, it's pi of theta, not pi of eta. So, well, it's not that funny because, it's useless. So it's easy to produce this kind of example where actually by using a very heavy machinery, you get up with a sample that at the end has not said anything about the information contained in the data. So convergence is really an issue, and not convergence in the asymptotic sense, but convergence in the tolerance sense. So let me show you just, well, I'll skip this example. Let me show you an example that is related with my talks, although it's a baby example in the sense that it's an MAQ model, so we know to handle an MAQ model. But let's look at the output to see the difference between the ABC outcome and a regular MCMC outcome, for instance. So we have an MAQ model where the connection between the data points in the series is through the noise. And we make a regular uniform assumption on the parameter theta I so that we get the classical identifiability conditions. Actually, in the case of an MA2 model, we just have a triangle around 0 for theta 1 and theta 2. So let's pick a uniform prior over that triangle. Okay. Now, if we want to apply the ABC example algorithm to this example, all we have to do is to pick a value of theta 1, theta 2 over this triangle. That's easy. And then we generate a new series by generating a new IID sequence of noises and constructing the series from the theta 1, theta 2, and the noises. Okay. Now, here comes a question of importance, once we have this pseudo-series and we have the original series, how do we compare both series? So the question is, how do we build the distance between the two series? Well, what we saw already in the simulated method of moment is that we could take the basic row difference between the two series by taking the sum of the xt minus x prime t squared. Okay. That's a distance. If it is 0, the two series are identical. Okay. There is nothing wrong with that. But that's using a distance between the series that contain a lot of noise in addition to information about the parameters. So an alternative is to try to reduce the dimension of the problem by looking for any type of estimator. How inefficient it is, it doesn't matter, but reducing the dimension as much as possible. So for instance, in MA2 case, we could take the two first autocorrelations and take the distance between those two autocorrelations. Here we have a distance in the space of dimension t, here we have a distance in the space of dimension 2. Those summary statistics are not sufficient, so in a sense we are losing information compared with that, but we will see that paradoxically we are gaining a lot. Because if we simulate ABC in both cases, those are the outcomes we get. If we use the distance between the autocorrelations, we get a quick concentration of the accepted values of theta 1 and theta 2. I mean, the triangle is the area of support of the prior. That's where the model is identifiable. And the colors blue, red, and gold are actually corresponding to tolerances of 10%, 1%, and 0.1% of the distances. So it's an empirical choice of the tolerance. That is the usual approach in ABC. And it's shrinking towards a point that is actually the MLE in that case. Okay, so it's shrinking in a proper region. Now, if instead I use the whole data to compute the distance, I get this very different picture where you still observe a kind of shrinkage from the prior towards the region of interest, but it's much, much slower, and therefore to get to region, and it doesn't look exactly the same, but it means that to get to regions that would be comparable in both cases, here we would need many, many, many more simulations. And if we look at the posterior, marginal posteriors for both approaches, if we use the distance on the raw data, we get this kind of behavior. Again, when epsilon is going down to 0, we get these three curves from flat to blue to red to gold. It is very far from the genuine posterior produced by an MCMC sampler. Same thing for theta 2. And the interesting thing is that as epsilon is shrinking, although the theory tells us that if epsilon is exactly 0, we should recover the true posterior, with 0.1% of the simulated distances, we are still very, very far from the true posterior. If instead we use the distance on the autocorrelations, of course we don't get exactly the true posterior, but we get a picture that is much, much closer to the true posterior. Granted, that's a fairly basic toy example, but we can get some conclusions out of that that will lead to the following points. First, as we saw the role of the distance, actually I should have said the role of the summary statistic, so we are just projecting first before computing the distance, is completely paramount. And the paradox of this role of the distance is that while the method is justified for epsilon exactly equal to 0, in practice we never get epsilon to be exactly 0. And the numerical value of epsilon is actually of little importance compared with the space we are working in. So epsilon is a relative value. There is no absolute epsilon in the real problem. But when we implement the method, it starts playing a role that is connected with the distance and the dimension of the problem. And this example is a perfect illustration of what has been called the curse of dimensionality for ABC algorithm. Namely that if we try too much by comparing the whole data with the whole pseudo data, although as statisticians, we would not want to waste any atom of information, in that case, the noise created by the simulation of the pseudodata is killing by orders of magnitude the information contained in the whole data. And therefore, it makes much more sense to first project in a smaller space, accepting that we are losing information, but then because we're in a much smaller space, epsilon will be closer to zero in this sense of bringing information. Okay? And so that's this paradox that we cannot only think as statisticians when dealing with this problem. We have to think as more advanced statisticians away from the true model. Okay, so let me go. I want to talk about the simulation methods, again, because there are several talks doing that in the sessions, and also because I'm not that much in terms of time. But some of the simulation advances have actually more to say about statistical inference than mere gains in efficiency. So one of the main points I want to stress before moving to the last part is that what I consider that the more legitimate interpretation of ABC is not a computational interpretation, but rather a non-parametric interpretation. It's like empirical likelihood, because we don't have access to the true likelihood. We are using those simulation methods to produce approximation to the true likelihood. And those approximations can be reinterpreted as non-parametric interpretation. So from the beginning of ABC, there were uses of non-parametric methods, especially in this important paper by Marc Beaumont and coauthors. But actually what's more important is that when we're using simulations from some transforms of the data through these summary statistics, we're actually trying to get to an approximation of pi of theta given eta of y. And being able to simulate these summary statistics is providing this kind of estimator. And that's how I made sense, for myself at least, of this curve for dimensionality. We are dealing with a non-parametric problem, and therefore we cannot hope with a given amount of computational power to get a good approximation of the whole posterior distribution of theta given the data. At best, we can get a few dimensions, because non-parametric estimation gets quickly terrible as the dimension increases. Okay, and so there are a few papers in the recent literature that explore this direction, and including Michael Bloom, who will give one of the talks in the ABC sessions. I won't say too much about that, but what ABC is doing is using one kernel or another. The basic kernel is indicator, is providing an estimator of pi of theta given eta of y using those simulations. And therefore, that explains how the error can be evaluated, namely that the range of the error is for the bias in terms of b squared, if b is the tolerance, and the variance is 1 over b delta d. And so the d is here, is acting upon the variance, and there is not much we can do as d increases, and except seeing the error increasing as well. Okay, so these are skip. It's really hard to skip MCMC, but I will. To move to the last part. And to go, it's more a review of literature than anything new, but I'm trying to replace ABC in the inference world rather than the computing world, again. So you may have seen this slide a few minutes ago, and just repeating the same thing, that so far, and we cannot get much further than that, ABC has been justified as a convergent method, or in some cases it has been justified as a convergence method. The simulation approximation method, it requires further simulations to give an evaluation of the approximation, except when we start looking at the non-parametric perspective, in which case we don't need to run more simulations. Now, while being pragmatic, it relies on a lot of calibration issues. We have to pick the summary statistics, and from there we have to pick the distances and also the tolerance. And in connection with the non-parametric perspective, and as stressed in the recent red paper by Paul Farnhead and Dennis Prangle, pushing epsilon exactly to 0, or as close as possible to 0, in that respect may not be the optimal idea, because we are losing intuitively a certain amount of simulations, but we're also increasing the variance by trying to reduce the bias. So if you're using ABC may be dangerous to your, maybe not health, but inference, without warnings from the general surgeon or whoever. Okay, so let me go through a few points, a few papers that relates to this idea. And one important paper in this respect is the PNS paper by Oli, Redman, and Corses, where because epsilon is both essential and a trouble nuisance, because it doesn't appear in the original inferential problem, they included epsilon into the picture by drawing inference not only on theta, but also on epsilon. Okay. And so they used a particular approach to do that by putting a prior on epsilon and transforming the likelihood into a function on epsilon. So epsilon became partly the error on the method and partly the variation of the pseudodata around the data. Okay, so because this is not exactly available, there is a non-parametric approximation involved at this level as well. And I mean, the technique, I won't go through the technique for lack of time, but it's using MCMC to move around with this trick that's all tricks. The first one is that the distances do not summarize into a one-dimensional object any longer, and that's the strength of the method. There are many distances altogether, and so epsilon becomes a multidimensional object. The distances can be negative, which is interesting for distances, but that's another positive point, being negative, right? And the last point is that because there are so many, there are several directions, the distribution on these directions are summarized into a minimum, which is another unusual object into the picture. And from this introduction of new objects, they get a way to compare models as well, because each of the directions, so this is stolen from the paper with permission, from each of the directions of the errors, you can build a distribution, a posterior distribution, or pseudo-posterior distribution of these errors, and compare what happens in different models to spot the model that is behaving strangely, namely is avoiding the 0 value that relates to our epsilon equals 0 justification of ABC. And I think I'll skip that, and we had a few questions, but I'll skip the questions as well. Now, another approach that started with Richard Wilkinson in 2008, but that has been found in many papers subsequently, is the fact that somehow ABC can be turned into what I call an exact BC, although it's not exactly an exact BC. Let me explain. When you look at this pseudo object that is connected with the product of our simulations, we are simulating from pi, theta from pi, then we are simulating pseudo data from the true likelihood, and then because we cannot wait, we have this weight that is 0 or 1 in the original ABC, or that is a kernel of any flavor in the general case, with a tolerance epsilon. So when you look at things from that way, this looks like a true posterior, but from another distribution than the true distribution. Namely, there is a convolution between the f and the k. You can look at f of z given theta times k of y minus z as a new distribution. Okay. And that means that ABC is exact, but for the wrong problem. Okay. So we're just asking the wrong question, but then we get the right solution. So if we do that, it's as if we were getting observations that are noisy. I mean, the true observation is y tilde from f of y tilde given theta, but then, because we don't observe y tilde, we observe y with noise psi from k epsilon, we do get this convolution term into the posterior. Okay, so in that respect, ABC is an exact Bayesian computation, but for a noisy model. And of course, this has drawbacks as a perspective, because rather than saying that it's measurement errors that would be fine, but to make it work, you have to say that it is a model error, and then using this k as the representation of the model error becomes difficult to justify in a conversation, right? So, of course, pros and cons to that. The cons are that it's still a fake model in that the k is totally artificial. You cannot start justifying that your normal or whatever kernel has anything to do with the truth. In addition, you have to modify the algorithm. Okay. Now, let me relate that to yet another paper where things get closer to the picture. It's a recent paper by Dean et al. Focusing on the specific model of hidden Markov models. So it also relates to Mike's talks, where you observe a sequence that is indexed by an unobserved Markov chain. And ABC in this setup is built in a way that the simulated data is forced to belong to an intersection of balls around the true data. So we only accept simulations where y1 is close enough to y1 not, the observed y1, up to yn close enough to yn not. So that makes for a very restrictive distance, because that's essentially comparing each simulation with each point in the series. And so it cannot work when n gets very large. But that's the price to pay for a series of interesting results that relate to both these aspects that ABC could be exact if we look at it from another side of the mirror, and also for its convergence when the length of the series goes to infinity. So again, they have the same remark that if you, for instance, define the ABC MLE, that is the first outcome of the simulation, trying to take the thetas that produce the highest rate of success in this acceptance. It is an exact MLE if we use a convoluted version, which in that case suddenly makes a bit more sense, because it's like you had the series and you drew a tube around the original series, and you could shake the series inside that tube. So you have a tolerance that is transformed into a measurement error of epsilon. In that case, for the noisy or shaky series, you get exact inference, and that's an error in observation type of model that starts being rather commendable. And there are different similar types of results, namely that if you look at the original model, ABC, even when n goes to infinity, ABC MLE is biased. But if you start decreasing epsilon towards a smaller value, you get this convergence to the information, to the converged likelihood as theta n, as n goes to infinity. So from this perspective, it's like replace the true data with this noisy version, and then you get regular Bayesian inference. And so that's one of the conclusions of the paper. And from there, we start saying where the connection between Bayesian inference and this ABC perspective could happen, namely that by accepting to throw away this precision on the data, you do recover an exact type of inference. Again, that's a bit against the original principles, that why should we throw away the information by roughening up the data, but that's the price to pay, that if we accept that we cannot get to this ultimate precision, that the whole information is not attainable, then why not doing that and still being Bayesian? And throw the A away, okay? And so in the paper, they do get a consistency result for the noisy version. Okay. Now, I mean, it's not like all nice and rosy. Things are deteriorating very quickly as n grows, because the paper is using a problem that is of dimension n, so this cannot resist the increase of n. But as a principle, I find the paper fairly interesting. I can't see. There are 2 5s, that means 10, right? Okay, now I just have 100 slides left, so I'm almost done. And I'll skip most of them. Now, I reached the final question, which is when we try to implement ABC, there are very few cases where we can use the whole data. So we have to pick a summary statistics because of the size of the data. There is no way we can produce a computable version without reducing the data into a small vector of summary statistics. And therefore, it's an interesting problem that we need to find in the optimal summary statistics for conducting this approximation to the true posterior. And there are cases where it's so relevant that, I mean, this choice of summary statistics, that depending on the choice, we do get consistency or not. And so we have a series of 2 papers, one of which Judith will present in a few days, where actually by picking the wrong summary statistics, the base factor when comparing 2 models will not be consistent. We will not pick, even when n grows to infinity, pick the right model, but we will pick the simplest model, for instance. And that for model choice, but of course there is the equivalent for estimation. And so in connection with that, there is, again, this red paper I mentioned a few minutes ago by Paul Van Head and Dennis Prangle that studies among all possible choices of summary statistics, which one makes the most sense for conducting ABC. And I won't discuss the paper, first because I don't have time, and second because this is not my paper, but the summary of the paper about the summary statistics is that the very interesting result and the very Bayesian result is that the optimal summary statistics is the Bayes estimator, E of theta given 1. And it has many interesting features. Well, first it's Bayesian. The second one is that it's exactly the dimension of theta. So you have not any extravagant entry in the summary statistic is just the barest possible entry. It's the psi of theta and nothing else. There is just one downside, which is that that's exactly what we try to approximate. So we don't have this summary statistic. And so in fact, to be pragmatic and practical, we have first to approximate this summary statistic before conducting the ABC. And the other part of the paper is that it deals with the errors contained in ABC. I mean, it's throwing away this idea that we are losing information by going from Y to this summary statistic, but otherwise it compares the approximation due to the convolution to the approximation due to Monte Carlo. And it recovers somewhere the non-parametric error I've already mentioned through this kind of evaluation of the error. It's somewhere, it's here. Yeah. So we do recover the non-parametric speed that we had previously. And then there is a side result that all Bayesians should appreciate, namely that if you use this as a summary statistic, it doesn't have to be sufficient, because you don't have to be in an exponential family model. But it is almost sufficient in the sense that the expectation of theta given S of Y is always the expectation of theta given Y. I mean, it took me a while to believe in that, but it's true. And so it's really whoa, okay? Now, it's not a perfect method, and I think I'll stop here. I had more about the discussion, but you can look at the slides on the web. The point is that through the recent literature, when statisticians became as interested in the method as population geneticists, it became obvious that there was more to the method than just a computational trick that looked fairly dirty. It's a way to handle complex models and to go over either the complexity of the data, the complexity of the parameter, or the partial information about the model. And my impression at the moment is that it's totally soluble in the Bayesian approach by rewording the whole thing as a new model rather than seeing it as an approximation to the exact model. Because in a sense, all models are wrong, but some models are useful. Well, some methods are more useful than others. Thank you.
Any questions? Oops.
It's okay, you can shout.
Any questions for Christian? Comments? We have some minutes time if somebody... You just believed it all. So in theory, I guess... some questions somewhere? Can you please go down to the microphone?
Hi. You mentioned that using Bayes factor may lead to picking the simplest model. Could you please explain it a little? You mentioned 2 references in 2012.
So there will be a talk on Wednesday on that paper. But essentially, if your summary statistic behaves the same or could behave the same under both models, then doing inference using only these summary statistics will lead to an agreement of the data with each of the models. Whether the model is true or not will not matter because you only look at the summary statistic. And so you will get an agreement for model A and for model B. And in that case, because there is agreement for both models, the one which wins is the smallest, the simplest one. So that's I mean, the core idea in this paper, that to make a discriminant separation between models using a summary statistic, it must behave differently under both models, so that you cannot recover the parameter under the wrong model.
Thank you.
Another question, Andres, or somewhere down there? Any other comments? Well,
Hi, Christian. Very interesting talk. In the tradition of looking at Bayesian modelling as a model for how rational people think, do you think that the ABC that you've been talking about could model how deterministic modelers try to get their models close to the data with noise, so some summary statistic of the data?
I've not thought about that at all. Just to make an objection for the sake of objection, as usual, I would say that the calibration then of ABC could get into the way by, I mean, the noise would be a choice of the statistician, not of the modeler, and so I mean, the choice of a kernel could just not get things right. I don't know. This could be an issue. But I mean, that's an interesting direction.
Left Christian speechless, pretty good. Any other comments?
I'm interested in some of the population genetics examples. So do you have any, in the light of your discussion of the different approaches and methods, can you sort of just say how good some of those previous results are, or are they sort of cast into question?
Well, let me answer another question. Just to link with the model choice issue, for instance, that a lot of the population genetic literature has been comparing scenarios. And of course, they used whatever summary statistics they had at their hand, right? When we looked at some of those papers, actually it happens that there were always a component in this summary statistics that was able to make the difference between the models. So although there was no formal checking that it was linked to the proper discrimination, in practice, in the cases we looked at, it was. It's not really answering your question, but...
Any more urgent questions? Otherwise, we have a bus to catch eventually. Let's move on. So let's thank Christian again. Thank you.